So acronym stands for Application Binary Interface, and Swift binaries interact with other libraries and components through an ABI. So we can say that it is a set of rules to which compiled binaries must conform to be linked and executed together. And why is that? Because binaries need to know how to call functions, how the data is represented in memory, and even where the metadata is and how to access it from the runtime. ABI is per platform, but Swift differs from languages like C or Rust, so most of its ABI is cross-platform. And since Swift 5, the Swift ABI has been stable, which means that the future will bring additive-only changes. So let's break Swift ABI to its components. Hello everyone. And Apple recommends to choose structs over classes whenever possible. Obviously, because they are value type, but what does it mean, and is it the only reason? My name is Jakub Kiermasz, and I'm a staff software engineer at SpotOn, and today we will go through Swift ABI components. We will explore how they interact with each other, and learn to benefit from it, and make your program even 10 times faster. So, if it sounds like a plan, please join me for the next 40 minutes. And we will reach that point by going through Swift compiler pipeline. We will learn what ABI is and its components. We will see how it affects Swift method dispatch. And finally, we will see some live examples. So, to write an application and meet the business requirements, you don't even need to know that the compiler exists. And the perfect example for that is the Playgrounds application for iPad. Basically, you click the run button and the magic happens behind the scenes. So let me assume that you know this particular fact. So how the heck has the Swift compiler works and makes your code into the executable program? At a high level, the Swift compiler follows the strict pipeline architecture. You should start by providing the Swift source code to the compiler, which is quite obvious, but then the parse module constructs an abstract syntax tree, and the SIMA module type checks the AST and annotates it with type information. Later, the Sirgen module generates raw Swift intermediate language, and a series of guaranteed optimization passes and diagnostic passes are run over the raw SIL to perform optimisations and emit language-specific diagnostics. And these are always run, which is crucial, even with disabled build optimization, and these produce canonical seal. Later, the general seal optimization passes optionally run over the canonical seal to improve the performance of your executable, and the decision, if it's run, is based on the optimization level. And the example is that when you pass the -on flag to the compiler, the optimization won't be run. And IRGen later lowers canonical seal to the LLVM intermediate representation. Finally, the LLVM backend applies its own LLVM optimizations and runs the LLVM code generator. And finally, it emits binary code, which is the result of the whole build process, and it's your program that you wanted to build. So, what part we will dive in? Basically, in other words, do we need to know all of this? So, looking into the parse, and SIMA won't give us many details, Sirgen produces raw, SIL, matching basic data flow and dispatch requirements. Then both diagnostics and guaranteed optimizations are applied even with disabled optimizations. And then general SIL optimization passes are run optionally. And we do not need to care about transformation to LLVM intermediate representation, since it has nothing to do with the Swift ABI itself, but with the LLVM. So we will cover only highlighted parts today. And let's start with Swift ABI. So acronym, as most of you know, stands for Application Binary Interface. And Swift binaries interact with other libraries and components through an ABI. So we can say that it is a set of rules to which compiled binaries must conform to be linked and executed together. And why is that? Because binaries need to know how to call functions, how the data is represented in memory, and even where the metadata is and how to access it from the runtime. So ABI is per platform, but Swift differs from languages like C or Rust. so most of its ABI is cross-platform. And since Swift 5, the Swift ABI has been stable, which means that the future will bring additive-only changes. So let's break Swift ABI to its components. Types must have a defined in-memory layout for instances of that type, and we name it data layout. Type metadata is used extensively by Swift programs, the Swift runtime, but even with the tools that all of you use, such as debuggers and visualizers. Functions must know how to call each other, and it was defined as a calling convention. Swift ships with a runtime library, and it handles such things like dynamic casting and reference counting, so this Swift runtime API is a big part of Swift ABI. Every exported or external symbol in a library needs a unique name upon which binary entities can agree, and MainLink handles it. And finally, the standard library with which Swift is shipped, and unlike C or Rust, once again, we cannot drop it, so it's always there waiting to be called. And that defines many common types, structures, and operations on these. And as you can see, these are split into the two parts. The one is on the blue background, and the other one is on the white background. And basically, when speaking of optimization of computer programs, only the two components which are on the blue background will give us the details we need, so we will dig only into these two. So, how to get the ABI details? Well, in computer science, when we want to explore a particular topic, the documentation is the thing we want to reach, right? But it should be easy. So I wish, because Swift missed a lot of documentation, and such crucial thing related to optimization and app performance as generic specialization still needs to be documented, and actually many more. So as you can see, it can be hard to be sure about Swift ABI and its requirements listed in the documentation. So it is time consuming, but I decided to dive into Swift compiler source code. But as most of you know, code analysis can be hard, especially if you didn't write this code. So I've created over a dozen test programs and analyzed the emitted SIL. And with such discovery, I can be sure that what I tell you today is 100% accurate. So let's start with data layout, also known as type layout. So it specifies the in-memory layout of an object's data. And these include size of an object in memory, the alignment of an object, and how to find each data member within an object. And we define two data layout types. The first one is a statically known, which stands for the object that has a statically known layout if the compiler can determine its layout at the compilation time. And alignment, size, offset, stride, all of that is known during the compilation time and is being used to create the other instructions. And all of these are not passed to the runtime. The second one is opaque, and it relates to objects whose layout is not determinable until runtime, and it occurs for unspecialized generics and resilient types. So this one is essential in Swift because of structs and the fact that they support protocol conformance even with extensions. And the data's layout is determined by accessing the value witness tables, which will be discussed in a few minutes, and the Swift runtime interacts with all the objects of opaque types through pointers, so it must be addressable, and it cannot be optimized. So for the partially known layout, there was an optimization discussion in 2017, which is still not resolved, so probably it won't be resolved at all, as well as there won't be detailed documentation of an ABI, but hopefully there will be someday. So now let's talk about existential containers that are strictly related to data layout. So values of protocol type, protocol composition type, or any type are laid out using existential containers. And the layout is known at the compilation time, so let's see how it looks. If there is no class constraint, which you can achieve by using any object on the protocol, or a protocol composition type basically, the existential container has to accommodate a value of arbitrary size and alignment. And it uses a fixed size buffer, 3 pointers in size, which is crucial, because this either directly contains the value if its size and alignment are less than or equal to fixed size buffer, or contains a pointer to a site allocation owned by the existential container itself. So the type of the contained value is identified by its metadata record, and witness tables for all of the required protocol conformances are included there. So now let's suppose one or more protocols in a protocol or protocol composition type have a class constraint, and only class values can be stored in the existential container, in such an existential container, and then like more efficient representation is used. And then we speak about class existential containers. And class instances are always a single pointer in size, so a fixed size buffer and potential site allocation is not needed at all. And these class instances always have a reference to the type metadata, so a separate metadata record is not needed as well. So let's take a look at the first code snippet today. So here we have protocol called swimmer, and then we have two structs conforming to it, duck and the fish, our brave swimmers for today. And array with objects of type swimmer with leverages polymorphism. So we cannot access them without casting by its structure types. So the array will contain the objects of protocol type by default when we access it. So here you can see the Swift intermediate language that was generated for this particular code. And the first highlighted part, which is the index address to store any swimmer. Later, the fish is initialized. And finally, existential container for fish with swimmer type is created. And finally, fish is stored at the existential container. So as you can see, the structs are stored via existential containers, not via the memory layout of whatever kind, or like, you know, that struct itself and its size. So it shows that the existential containers are used even when we speak of structs which are value types. So while data layout specifies the layouts of objects of given type, type metadata holds the information about the types themselves. And we can speak about value types metadata. And it has kind-specific entries, which means that it contains different information for every kind of type. And what are kind of types? Basically, we can distinguish a few. So structs, tuples, enums, which are not indirect, and all the values that are value types can be distinguished when speaking of kind of types in this case. And every concrete type has a value witness table that provides information about how to lay out and manipulate values of that type. And when a value type has opaque layout, the actual layout and properties of that value type are not known at compilation time, so the values witness tables is consulted. And we can distinguish another one, which is class types metadata. And this one had to be layout compatible with Objective-C from the beginning, on Apple's platform specifically, which places requirements on the contents of the first section of class metadata. And in this first section, entries such as superclass pointers, instance size, instance alignment, flags, and opaque data for Objective-C runtime are stored. And following that are superclass members, parent type metadata, generic parameter metadata, class members, virtual tables, etc. So as you can see, it can become a really big boy. And the third one and the last one are protocol and existential metadata. And the protocol witness table is a function table of the types conformance to the protocol's interfaces. And if the protocol also has an associated type requirement, then the witness table will store the metadata for the associated type. A protocol descriptor describes an individual protocol constraint, such as whether it is class constraint, the size of conforming witness tables, and protocol descriptors for any protocols it refines. And there are also metadata details for functions, generic specialization, and so on, but we cannot leverage them in the decision process. So what I want you to learn from this part is that things look different under the hood, and value tables, we know from Swift, have associated tables when needed, and types that can be queried. So is actually the same thing for protocols. So because of all that, always think about how your code behaves on lower levels. And now we can move to method dispatch. So with all the knowledge we gather, we can even use it. And, but I want you to keep one sentence in mind before coming to the next section, and it is the more restrictive code comes to the compiler, the more performant it is at runtime. And we distinguish two method dispatch approaches. The first one is static, which is also called direct. So in this case, the compiler does know which executable code should be used, and it's the fastest style of method dispatch, and it requires a minimal set of assembly instructions. Moreover, the compiler can apply optimisations like inlining the code. And it does not allow polymorphism, since such is known mostly since runtime. And here we can see another example, and in this case it is static dispatch optimization, which is inlining in this case. So we have a structure called SwiftHeroes with one getter method, and then it is accessed to print this value. So the optimized version looks following. We simply create the memory to store the value, and the value is put into the Swift intermediate language directly, which means that we don't need to access the structure, which is exactly what inlining is. And here then we create the storage for that, and it will be put later. And in not optimized version, we can see that we need to create the struct. We then access the struct and extract the value of the structure, and finally we can store it and pass it to the print function. So as you can see, with inlining the code and optimization of static dispatch, we can omit creating the whole structure, which can be time-consuming when it is larger than one getter function. And now let's talk about method dispatch for extensions. And every method declared inside extension is dispatched statically in Swift, but as object subclasses, but let's not dig into that, and which obviously uses message dispatch, which will be discussed soon in general. But we'll base the analysis on that code in this part. So here we have protocol called conference, an extension to that protocol, and later we have a structure that conforms to the protocol conference, and later we have the property with type conference. So when we access it later, we are accessing it, but the conference type, not but the struct type, which is a SwiftHeroes. So the optimized version in this case looks following. There's a suggestion for a compiler, basically for the LLVM backend, to always inline this code. Swift CLGen applies the optimization, which is guaranteed to be run even when we disable optimization, and it puts the always inline suggestion for the LLVM backend. And when speaking of not optimized version, here in the code when we've inlined a version, basically we will put the code from the function. Here we have to create the function reference, apply it to the structure we created, and as you can see, the function which is defined in the extension itself does not have the always inline suggestion for the LLVM backend. So now we can talk about the other method dispatch, which is dynamic in this case. So it is exact opposite of static dispatch, and the compiler does not know which executable should be used, so it has to be determined runtime. And the runtime library looks for a specific method implementation, for example, by tables. And because of this, polymorphism is available. And the first implementation we'll dig into is table dispatch. So table dispatch is the most common method of dispatch among compiled languages such as C#, Java, and Swift. And the compiler does not know which executable code should be used for a particular method code. So this decision is taken at runtime. And class have virtual tables with arrays of function pointers to its methods. And every subclass has its own copy of virtual table with different function pointers to those methods which are overridden. and when a subclass adds a new method to its definition, the method is appended to the end of the corresponding table. And the compiler builds the tables, and at runtime, the tables are used to determine which method should be called. So, another code example, we have two classes. The first one is parent, the second one is child, which inherits from parent. And in the parent, there is the foo function declared, and in the child, we override this function. In the parent, there is go function as well, and in the child class, there's the who function, which wasn't declared at the parent class. So, the tables will look following for them. As you can see, the foo function has a separate pointer in both cases. The go function in the parent points to the parent, but in the child, it points to the function which is declared as in the parent's body, and the who is only available from the child virtual table. And to see how tables look in Swift intermediate language, we can analyze simpler case with one protocol and the function which will be implemented in the class that conforms to this protocol's interface, basically. So, the Swift intermediate language in this case looks following. We have a virtual table for the class you've seen before, and we have the witness table as well. So as you can see, the polymorphism will be accessed by two tables. The one which is virtual table for classes, and when we access it via the protocol, it will be the witness table. And as said before, existential containers store protocol or protocol composition type values alongside corresponding witness tables for each protocol conformance. And a type's conformance to a protocol consists of functions, whether they are methods, getters, setters, whatever, and the specific addresses of those functions are not known at compilation time for existential values, as the actual type is not known until runtime. And this is a similar situation as with references to non-final classes, non-final class instances actually, and is solved using a similar technique. So protocol witness tables are tables of function pointers implementing protocol conformance. And once again, let's take a look at our brave swimmers from today. So we have protocol with one function that is implemented by the structures, and here we can see that there are two witness tables because we have two different types, which are structures in this case, conforming to this protocol, and this is how the protocol conformance and polymorphism is achieved. So previously, I've said protocols extensions are statically dispatched. And what does it mean? Basically, let's analyze another code we generated for our Swift source code. And here you can see the protocol called conference, and there's an go function in the extension, which is not in the interface of this protocol, which is crucial in this this part. And we have the go function as well in the structure called SwiftHeroes, which conforms to this protocol, but it's not the part of this of its interface. So we can create an object of the SwiftHeroes type, and then we can call both functions, foo and go in this case. And the result will be following, and it is because we are accessing it by struct type, not the protocol type. So the result will be SwiftHeroes foo and SwiftHeroes go. And when we call it via the protocol type, which leverages from polymorphism, the result will be following, and it is SwiftHeroes foo and conference go, and it is because we have no chance to get an info about go function from the structure because we are accessing it by the protocol type, and the go function is not part of its interface, so it's statically dispatched from the protocol extension. So now let's talk about method dispatch that came to us from Objective-C, and it's another implementation of dynamic method dispatch. In this case as well, the compiler also does not know which executable code should be used. So a key point of method dispatch is modifying the dispatch behavior at runtime, which can be both awesome and dangerous. So method swizzling allows exchanging the implementation of two class methods at runtime. And this will affect every instance of modified class. And which was or will be created. And basically, this is how most of analytics libraries work. And because of dispatch being based on a tree, ISA Swiftling is possible, which is basically the change of an object's type at runtime. So let's take a look at another example. Here you can see the example you've seen already before, but slightly modified because in the class parent, these two functions are marked as dynamic, which exposes them to be dynamically dispatched in Objective-C. And later you have the class called child, which inherits from the class parent, and the function foo is overridden, but the who is added, so it won't be available in parent class. So now let's take a look at the function tables for these two classes. As you can see, child has the who, parent does not have any who pointer, but child has not go pointer as well, which slightly differs from what we have in virtual tables when speaking of dynamic dispatch in Swift directly, because there's an algorithm that finds the function we want to call at the runtime. And Swift builds this hierarchy as a tree structure and puts it into some static memory region. So when a message is dispatched, basically, which means that the method is called, the process will try to find the function pointer of the method in the child class table, and if the function pointer is not found, we will jump to the parent. But if it's not, if it is, it will basically call this function. And if it's not, once again, we will go to parent and repeat the previous steps until we find the function pointer or the root class is reached, and then bad thing happens. So, how to suggest the compiler what to do by using dispatch behavior modifiers? The first one is final, which probably most of you know, which enables static dispatch, removes the possibility of any dynamic behavior, hides the method from Objective-C runtime, denies inheritance, makes class methods to be called via static dispatch, compiler to make some optimisations, and it is related to classes only from obvious reasons. The second one is dynamic, which enables method dispatch on a method, and before Swift 4, it was exposing to Objective-C runtime immediately, but now it's not. And it as well relates to classes only because struct does not support inheritance. The third one is add Objective-C, which does not alter method dispatch and makes the method visible for Objective-C runtime. And the perfect example for that is selectors that you use when you use the UI kit in old style. And how does it work? Basically, it takes the, what is selector? It is the string that represents this function, and this is how the Objective-C runtime is accessing it. So it do not need to be dynamic when we need to call it via without the inheritance in other classes. The fourth one is non-Objective-C, which is same as final, so it's quite funny because it is redundant. And the fifth one is add Objective-C final, which is pretty powerful because it enables direct dispatch on the method and registers the method selector at Objective-C runtime. So it responds when performing a selector or another Objective-C feature with giving the performance of direct dispatch. And the last one is inlining, which slightly differs from previous ones, and it is because it takes parameter, and we can pass two parameters. One is never, and one is always, and they probably speak for themselves. But also, you cannot be sure that the inlining will be applied or not, because it is only the suggestion for the compiler. So in most cases, it will be inlined if you say so, but there are some situations when it will be ignored. So now let's see some live examples. Okay, so the first program that I want to dig into with you, let me just, because the screen, oh, maybe here, okay. So it's about function specialization, and we have a protocol called testable with final class called testing class and another structure called testing structs. These two conforms to this protocol. Later we have some helper functions to measure the time it will take to perform this particular part of code when we basically store the objects to an array, and we will compare two versions. The specialized action, when the type is specialized by using generings, and the unspecialized action where the type is erased and we access the objects via protocol types, and we will run it with the object passed before the action that we want to measure to just focus on how long it will take to store them and ignore the initialization of these two. So let's run it. And as you can see, the specialized function calls for class, okay, now you can see. For classes, is almost 1.5 times faster than unspecialized, and the specialized function call for struct, it's almost 10 times faster than unspecialized. But I promised you something before, so sometimes it can be even 10 times faster, 11 times faster. Once I achieved even 12 times faster code when run another time. So as you can see, it is because we know the type itself, and it's when we speak about specialized action, we know its layout when speaking of data layout, and with the unspecialized we are not, so it has to be calculated and computed. Another example I want to analyze with you is related to inheritance. So we have a class called building, we have another class called house, and a bungalow, and all of them have the same body, which is basically like creating a string and dumping it. So here the house inherits from building, and the bungalow inherits from house, and the building obviously because of how it works. And once again, there's the same helper function which measures the time, and basically a few times we access this method. So let's run it and see how it will work without any specifiers that we have learned about before. So it will take about 3 seconds probably. It's quite laggy. Okay, so as you can see, the times are pretty much the same. And this is because the value tables, virtual tables related to classes are pretty short in this case, and these are pointers. So the pointer directly points to the method, so it's not a big deal to access it. So don't be afraid to use classes, but we can make it a little bit harder for our computer by exposing it to Objective-C and make it dynamic to see how it will affect the runtime. So let's run it again. And as you can see, the times are bigger, and we can make them faster in just one class. So here we can modify it by adding the final specifier to this class. And you can see that it is faster. So remember, when there is the Objective-C exposure in the class that you don't want to touch because it has 2,000 lines of code and you are afraid to change anything in that class, the final in the class that you want to create and inherit from another can be a solution. Because this is pretty small one, but when speaking of a bigger one classes, it can be a big deal. And the third example is the smallest one. So we have a protocol called operation, and we will access this function by using the protocol type and the structure type which conforms to the protocol, and the bodies are the same, and we will see how they differ from each other. So let's run it, and as you can see, protocol's extension function is over 100 times faster than access by protocol interface. And now I can run it again, and you can see, it's always performed like faster than the access by protocols interface, and this is because we can like this is because it is statically dispatched. So when there's no need to like reuse the method declared in the protocol, and you don't want to redefine it whenever you conform to the protocol, the extension can be pretty powerful, and like it's almost 100 times faster, and sometimes it can be like even bigger deal. And when I disabled the debug, it took 0 seconds. And why is that? Because compiler sometimes create, sometimes apply the pre-computation. And what does it mean? Basically, a compiler, without running the code, calculates the result of your program and put it directly into the code, so it's kind of inlined and calculated by the computer. So it can be like really powerful when we think about how the code behaves in the lower level. So that was it from my side. If you have any question, now is the time. And all the snippets, all the code that I used to analyze the seal is available at my GitHub, so you can scan the code and like check it out later. And if you don't want to ask the question now, you can reach me later via this link.
Thank you very much, Jakub.